Today, we're going to pull back the curtain on how professional engineers build software that actually works. We're talking about a framework they use called the pyramid of quality. It's the secret sauce that keeps the apps you use every day from completely falling apart. So let's get into it.
But first, a question we've all asked. Why is it that you can download a brand new, super expensive piece of software and it still has bugs? We've all been there, right? It's so frustrating. The short answer is complexity. Modern software is just a tangled web of millions of moving parts. And that's exactly why having a structured plan for testing isn't just a nice to have, it's absolutely essential.
So here's our game plan for today. We're going to climb this pyramid together, step by step. We'll start at the bottom with the foundation, then we'll move up to see how all the pieces get connected. After that, we'll test the whole thing as one big system, and then we'll focus on hardening its defenses. Finally, we get the user's opinion before we wrap it all up. All right, let's kick things off with Section 1, the foundation of quality. You know, just like with a building, you can't have a sturdy piece of software without a rock-solid foundation. And in our world, that means starting with the smallest, most basic pieces of code.
Now, this pyramid is our roadmap, and you'll notice its shape is really important. The base is super wide, right? That's because it represents thousands of tiny, super fast tests called unit tests. As we climb higher, the tests get bigger. They cover more and more of the system, but they also get slower and way more complicated. So naturally, we do fewer of them. The key takeaway is this. Quality is built from the ground up, starting with this huge, solid base.
So let's talk about that base, unit testing. This is our first line of defense against bugs. We're not looking at the whole app here, not even close. We're using a microscope to zoom in on the smallest possible bits of code, like a single tiny function. Think about it like building a house. Before you even think about putting up a wall, you check every single brick to make sure it's not cracked. That's a unit test. And who writes these tests? Well, the programmers themselves. It's a way for them to double-check their own work. They're asking questions like, does my sorting algorithm actually sort things correctly? What happens if someone tries to enter a negative number or a word where a number should be? That's called testing the boundary conditions. So for our example, the register student function, we test it all by itself, completely cut off from the database, the network, everything, just to be sure it does exactly what it's supposed to do, no matter what.
Okay, so our individual bricks are solid. We've checked them, we're confident in them. Now it's time to start putting them together with mortar. This is the next level up the pyramid, where we move from a pile of parts to an actual working machine.
Welcome to integration testing. We already know our individual parts work in a vacuum, but what happens when they have to talk to each other? That's what we're testing here, the connections between the components. It's like in our house, we're not just checking the sink and the pipes separately. We're checking to make sure the pipes are actually connected to the sink and don't leak. Trust me, these connection points, this is where things get really interesting. And I really want you to remember this next point because it's a big one. While those little unit tests are great for catching simple mistakes, the trickiest, nastiest, most painful bugs, they almost always show up during integration. Why? Because you're taking code written by one person with their own set of assumptions and trying to connect it to code written by someone else with their own assumptions. When those assumptions don't line up, that's when you get big problems. Now, to handle this mess, you've got two basic strategies. The first is what we call the Big Bang approach. It's basically where you build everything in separate little silos, and then, at the very end, you just smash it all together and pray that it works. Yeah, it's usually a recipe for absolute chaos. The much smarter way is the incremental approach. Here, you add one new piece at a time, testing each new connection as you go. And the advantage of going piece by piece is just so obvious. When you add one new thing and suddenly everything breaks, guess what? You know exactly where the problem is. It makes finding and fixing bugs 1,000,000 times easier. Plus, there's this huge psychological win. The system is always sort of working, which keeps the team's morale up and shows everyone that you're making real progress. All right, so the individual pieces work, and the connections between them are solid. Now it's time to step back, zoom out, and look at the whole shebang. We've built the house, but does it actually function as a home? This is system testing. At this stage, we stop looking at the internal code. We treat the entire, fully built piece of software as one giant black box. The person testing it doesn't know or care how it works on the inside. They're just acting like a real user would.
They're testing a full journey from start to finish against the technical requirements. For example, can a user log in, find a product, add it to their cart, and actually pay for it? It's all about making sure the system as a whole does what it's supposed to do.
And system testing isn't just one thing, it's a whole category of tests. You've got performance testing to see if it's fast enough, stress testing to see how much pressure it can take before it breaks, recovery testing to see what happens if it crashes. And then there's a really important one called regression testing. This is where you're constantly asking, hey, that cool new feature we just added, did it accidentally break 5 old things? Each of these tests is checking a different angle of the system's overall quality.
Now, of all those different system tests, there's one that has become more and more critical in our super connected world. So let's take a moment to do a deep dive into how we harden the system's defenses.
One of the best ways to do this is with something called penetration testing, or pen testing for short. This is basically ethical hacking. You literally hire security experts to launch a full-on simulated cyber attack against your own system. Their job is to think like a bad guy, find all the weak spots, and break in, so that you can fix those security holes before a real attacker finds them.
And you can do this in a couple of ways. In a white box test, you give the good guy hackers the full blueprints to your system. All the source code, all the diagrams, everything. This lets them do a really deep, thorough check. But in a black box test, you give them nothing but the public web address. You make them act just like a real attacker would, with no inside info. The best security plans, they use a mix of both to find all sorts of different weaknesses.
So what's the payoff? I mean, is this really worth it? Well, check out this number. A case study on a big manufacturing company found that a single pen test discovered issues that, if exploited, could have cost the company over $2.5 million per day. We're not just talking about theory here. We're talking about protecting the entire business.
Now, a great partner to the targeted approach of pen testing is something called fuzzing. Fuzzing is basically automated chaos theory. You use a tool that just bombards your application with millions and millions of pieces of random, bizarre, broken data just to see what makes it crash. It's surprisingly effective because it finds bugs that no human would ever think to look for, but that a clever attacker could definitely take advantage of.
Okay, we have made it to the top of the pyramid. The foundation is solid, the parts are connected, the whole system has been tested, and we've locked all the doors and windows. There's just one thing left to do, the final walkthrough with the person who's actually going to live in this house.
This final step is called acceptance testing, and at this point, the whole perspective shifts. We are no longer asking if the software meets the technical requirements, or asking if it meets the business requirements. The final question, which can only be answered by the actual customer, is this. Does this thing you built for me actually solve my problem? Because a piece of software can be technically flawless, but if it doesn't solve the right problem for the user, it's still a failure. This is the last checkpoint before it goes out into the world.
So we've climbed the entire pyramid. And what you should realize is this isn't just a one-and-done checklist. It's really a continuous cycle, a process that systematically builds up our confidence that the software we're about to release is ready.
This table really pulls it all together perfectly. We start at the bottom with a developer testing one tiny register student function all by itself. Moving up, we test how that function connects to the database. Then, a QA team tests the entire user experience, from logging in to checking out. And finally, at the very top, the actual customer asks a real-world business question like, can my users sign up for 3 events at once? See how the scope gets bigger and bigger, and the person doing the testing changes as we move from the developer all the way up to the end customer? This whole process, this pyramid, it builds a massive amount of confidence and dramatically lowers the risk of shipping a broken product. But it does leave us with a final thought, doesn't it? This pyramid helps us get pretty close to perfect, but can any amount of testing ever guarantee it? And looking ahead, how is something like AI going to change this whole game? Will it automate it, speed it up, or maybe even flip this entire pyramid on its head? That, my friends, is a question for another time.